This is the video for section 11.11 on applications of Taylor polynomials. And this video should be considerably shorter than the last one. So the idea of this section is this, and we're only going to do half of this section. This course we're going to skip the applications to physics, and we're just going to focus on the approximation properties for Taylor polynomials. So the idea is, if I have some function f of x that's represented by its Taylor series, right? So that means that I have a function f of x that's represented as this infinite series near some values of x equals a. And what that means is that the function can actually be approximated by partial sums. So for instance, when n equals 0, this just says that f of x is approximately the same as f of a nearby that point. So this isn't the greatest approximation, but it is a true statement. To get a better approximation, we take n equals 1, and that says that f of x is approximately f of a plus f prime of a times x minus a. And this is the linear approximation that we learned about in Calc 1. And when we take n greater than or equal to 2, we get better approximations. Okay. And what we're going to do is we're going to use Taylor's inequality to see how good these approximations are. Okay? And if you like some visual representations of this, you should look in the book that contains some graphs for e to the x and its Taylor polynomials, Tn of x, so that you can see how this approximation process looks graphically. So I want to do one example here. So I want us to find the Taylor polynomial of degree 3 of the function f of x equals ln of 1 plus 2x. And we could do this by substituting into the Taylor series that we found in the previous section, but instead I'm going to do this at the point a equals 1. And then we're going to estimate the accuracy of the approximation of this function by its third Taylor polynomial on the interval from 0.5 to 1.5. Notice that this is an interval that's centered at my point a equals 1. So in order to find the Taylor polynomial, I need to take some derivatives. Let me spare you the gory details about this. When I take f of 1 is just going to be ln of 3. F prime of 1 is going to be 2/3. F double prime of 1 is going to be negative 4/9, and F triple prime of 1 is 16/27. So this tells me, remember, that in order to find the coefficients for my Taylor polynomial, I need to take these derivative values and divide by the appropriate factorial. So C0, I don't do anything, I just take that function value. For C1, I take my function value and I divide by 1 factorial, so that's just 2/3. For C2, I take that derivative value and I divide by 2 factorial, so that's going to give me negative 2/9. And for the third coefficient, I'm going to take that derivative value and divide by 3 factorial, and when I simplify that, I get 8/81. And so from this, it follows that the third Taylor polynomial at a equals 1 for this function is going to be ln of 3 for my constant term, 2/3 times x minus 1 for my linear term. Notice again I'm using the point a equals 1. I subtract now 2/9 x minus 1 squared, and I add 8/81 x minus 1 cubed. Okay. So this is the first part of us finding T3. And on the next page, what we'll do is we'll use Taylor's inequality in order to estimate the error by approximating from the Taylor polynomial. So remember that Taylor's inequality says that if the absolute value of f to the n plus 1 of x is less than or equal to m whenever we have absolute value of x minus a less than or equal to d, then I get to conclude that the absolute value for my error is less than or equal to m over n plus 1 factorial times the absolute value of x minus a to the n plus 1. So as we did in the previous video, we have to find out what the m, the n, the a, and that such is in our situation. So remember that we have a equals 1 and f of x equals ln of 1 plus 2x. I'm going to need to take the fourth derivative of this function, which I have done. So if you work it out, the fourth derivative of my function is going to be negative 96 times 1 plus 2x to the minus 4. And so when I take the absolute value of that, I get 96 times the absolute value of 1 plus 2x raised to the negative 4 power. Now, remember that we are looking at the interval from 0.5 to 1.5, and that means that when we look at the number line, here's 0, here's 1, where the center of my Taylor series is, I have 0.5 here and 1.5 here. The absolute value of x minus a, which is in our case absolute value of x minus 1, is less than or equal to 0.5, right? That interval has radius 0.5. Now, because I have all positive values for my x, this absolute value here will go away, so we get 96 times 1 plus 2x to the minus 4. And the thing that you should note is that this function is a decreasing function. And so its maximum value, which is what I'm interested in, occurs at the left-hand endpoint of the interval, which is x equals 0.5. And that tells me that on the interval that I care about, this derivative that I'm investigating, and remember that I'm looking at t3, so I have n equals 3 in my Taylor inequality, that this is less than or equal to 96 times 1 plus 2 times 0.5 all to the negative 4 power. And that simplifies to 96 times 2 to the negative 4, which is the same thing when you work it out as 1 over 64. Sorry, it's equal to 6. I jumped ahead in my notes. So what Taylor's inequality, so what I've concluded, if you compare with the hypothesis of Taylor's inequality, that I have shown that the absolute value of that derivative is less than or equal to 6. So this is my m value in Taylor's inequality. So Taylor's inequality tells me that the error in absolute value is less than or equal to 6 over 4 factorial times the absolute value of x minus 1 to the 4th power. And so when we simplify that, that's the same thing as 1/4 times the absolute value of x minus 1 to the 4th. And this is going to have its maximum at the right-hand endpoint for our interval, which is at x equals 1.5. And so we conclude that this is less than or equal to 1/4 times 1.5 minus 1 to the 4th, and that is what simplifies to 1 over 64. So the conclusion that we have from Taylor's inequality, again, that our error using the third Taylor polynomial to approximate our function is at most 1/64th. And you should look in the textbook at examples 1 and 2 for more examples of this. And this is the end of the video for section 11.11.